previous class we have seen CVSL logic. Many were absent, so you can go through the video where I have explained how the actual circuit behaves or how it functions. Next, coming to the electrical and physical connections or design of the basic circuits. So this is the schematic of inverter, which we have already seen. Okay, and what they have given here is how it is basically constructed, how electrical connections are done, and physically how they are linked to each other. So as you can see here, we have a P MOSFET and a N MOSFET. Then we need to connect the source terminal of the P MOSFET to VDD. Therefore, we have an electrical connection here. We need to short the drains of both P MOSFET and N MOSFET mutually. Therefore, a connection is shown here between drains. And also the source of the N MOS should be connected to ground. Again, an electrical connection is shown here. Okay. So this VDD is shorted. So basically what we are seeing here is the physical and electrical design of gate. This is not gate. Okay. The same way we can have different gates, and this is the actual physical design which we do in the lab. So these two are the layouts of inverter. Right? Both the layouts are correct. Why both the layouts are correct? Because you can just verify. This layout we have studied it in our previous classes. So this is P diffusion, this is N diffusion, this is poly. So when poly crosses the P diffusion, it forms the P MOSFET, and when poly crosses N diffusion, it forms the N MOSFET. So this is N MOSFET, this is P MOSFET, and this is our VDD and VSS. So as usual, as per our schematic design, we are shorting the source of P MOSFET to the VDD. Drains are mutually connected. Source of N MOS is again going to ground. And the drain which is shorted, there we are taking the output and the input. Okay. What we are doing for the input, actually we can have one poly here and one poly here separately. But we know that both the gates should be shorted. Therefore, we are keeping common poly which can be called as input. This thing we have seen in previous class, where I had explained you how to draw the layers. This was shown. But coming to this part, now the P diffusion was horizontal. There we have done it vertically. And the poly was straight, poly was vertical. There what we have done, we have made it horizontal and then we are shorting. Okay. So just we are interchanging the positions of P diffusion and N diffusion followed by poly. And as I said, both the layouts are correct. Now the question comes, why there are two different layouts? Okay. So actually there is no any hard and fast rule that I have to draw like this only or like this only. It depends on the situation. We can choose any of these, or we can choose the third one also, which is not shown here. Okay. Actually, we can see few more. So this is one scenario where I need to pass metal 1 layer through this layout. See, there is some scenario where this is a layer, inverter. Okay. Before this inverter, you think that there is some circuit. Imagine some circuit is present before this inverter. Okay. And there is a need of passing the two metals, these two metals, ಅವು ಎರಡು ಮೆಟಲ್ಸ್ ಹಿಂಗೆ ಪಾಸ್ ಆಗಿ ಮುಂದಿನ ಸರ್ಕ್ಯೂಟ್ ಕನೆಕ್ಟ್ ಆಗಬೇಕು. those two metal layers should be passing through the inverters. That is the need of the hour. In that case, what I can do, I need to choose metal 2 here. And then is up to bigger. See, actually this is field diffusion and diffusion. Okay, this is poly. Right? And if I short the drain to drain with metal 1, then I cannot pass this metal with this metal because both the metals will short. Okay. So E metal here pass that should not be shorted with the drain. Therefore, what we are doing here, we are making use of some different layer. So here we can use metal 2. Okay. This can be metal 2. So here they are using via. So metal 1 converted to metal 2 via again is converted to metal 1 again. So here what we are doing, we are passing the two layers of metal 1 through the layer of inverter. Okay. So if we want to pass some poly through it, either through poly pass ಮಾಡಬೇಕು, then it may differ. Okay. See here, this case. E case ಒಳಗೆ ಏನಾಗಿದೆ? E case ಒಳಗೆ we want to pass two polys through the inverter. ಅದು ಯಾಕೆ through ಅಂತ ನಮಗೆ ಗೊತ್ತಿಲ್ಲ. ಯಾಕೆ ಪಾಸ್ ಮಾಡಬೇಕು ಅಂದ್ರೆ ಪ್ರೀವಿಯಸ್ ಸರ್ಕ್ಯೂಟ್ ಒಳಗೆ ಎರಡು ಪಾಲಿ ಅದಾವ. ಆ ಪಾಲಿ ಮುಂದಿನ ಸರ್ಕ್ಯೂಟ್ ಕನೆಕ್ಟ್ ಆಗಬೇಕು, ಬಟ್ ನನಗೆ ಇನ್ವರ್ಟರ್ ಬಂದದ. But still, the condition is I have to pass two polys through this inverter. Therefore, I should not be having poly in this region where I am passing the two different polys. ಮೊದಲ ಸರ್ಕ್ಯೂಟ್ ಇದೆ ಎರಡು poly ಪಾಸ್ ಮಾಡ್ತೀನಿ. ಈ ಸರ್ಕ್ಯೂಟ್ ಇನ್ poly ಶಾರ್ಟ್ ಆಗಬಾರದು. Therefore, what we do, we choose a different layout now. This is the poly. This is the poly. So, ಇಲ್ಲಿ P MOSFET ಆಯಿತು, ಇಲ್ಲಿ N MOSFET ಆಯಿತು. As soon as we form the MOSFET, ಏನು ಮಾಡ್ತೀವಿ ನಾವು? We will use via. Okay, bridge, over bridge. Flyover ಮಾಡ್ಬಿಡ್ತೀವಿ ನಾವು. ಈ poly ಹೋಗ್ಲಿಕ್ಕದ. So, ಇಲ್ಲಿ poly ಬಂದು from via what we do? We will switch it to metal 1 and this metal 1 passes here. Again, this is poly. Okay. So poly is not poly is short agate. Therefore, we choose one more wire. So these two polys can be easily passed. So these are some practical scenarios wherein we want to adjust the connections. Okay. These things you will practically do it in the lab. If you are interested, you can take up some projects also. You can learn minute things. And one more fact I will tell you. There no blank space is not. This blank space is either those spaces are called as white space. Okay. So a good layout designer is the one who keeps white spaces minimum. ಈಗ ನೀವು ಮನೆ ಕಟ್ತೀರಿ, ಮನೆ ಕಟ್ಟುವಾಗ 30-40 ಸೈಟ್ ಐತಿ. 30-40 ಸೈಟ್ ಒಳಗೆ ಅರ್ಧ ಜಾಗ ವೇಸ್ಟ್ ಮಾಡಿಬಿಟ್ಟ ಅಂದ್ರೆ ನಾವು ಅರ್ಧ ಜಾಗಕ್ಕಷ್ಟೇ ಮನೆ ಕಟ್ಟಿದ ಅಂದರೆ ಸೊ ನೀವೇನು ಹೇಳ್ತೀರಿ, ಪೂರಾ ಮ್ಯಾಕ್ಸಿಮಮ್ ಏರಿಯಾ ಪೂರಾ ಯೂಸ್ ಮಾಡುವುದು ಅಂತ ಹೇಳ್ತೀವಿ. In the same way here, if I have this much area, it should be utilized very fruitfully. Or in the other case, in other words, ಇಷ್ಟೇ ಏರಿಯಾ ತಗೊಂಡು ನೀವು ಡಿಸೈನ್ ಮಾಡಿರಿ ಅಂದ್ರೆ a good layout engineer, what he will do, he will think of designing the same circuit in half area or lesser area. ಇದೇ ಸರ್ಕ್ಯೂಟ್ ಇಷ್ಟೇ ಏರಿಯಾನ ಕಂಪ್ಲೀಟ್ ಮಾಡೋ ಅಂದವ, ಇಷ್ಟೇ ಏರಿಯಾನಾಗ ಎರಡು ಸರ್ಕ್ಯೂಟ್ಸ್ ಕೊಡ್ತಾವ. ಸೊ ಎಫಿಷಿಯನ್ಸಿ ಜಾಸ್ತಿ ಆಗ್ತದೆ. compactness increases. Although your device gets smaller and smaller. This mobile phone ಐತಿ ಈಗ ಇದೇ ಮೊಬೈಲ್ ಫೋನ್ ಇಷ್ಟೆಲ್ಲ ಫೀಚರ್ಸ್ ಇಟ್ಕೊಂಡು ಓಕೆ 20 ವರ್ಷ ಮುಂಚೆ ಮ್ಯಾನುಫ್ಯಾಕ್ಚರ್ ಮಾಡಿದ್ರ ಈ ಮೊಬೈಲ್ ಫೋನ್ ಇಷ್ಟು ಇರ್ತಿದ್ದಿಲ್ಲ, ಇಷ್ಟು ದೊಡ್ಡದಿರ್ತಿತ್ತು. ಹಿಂಗೆ ಹಿಡಿದು ಮಾತಾಡಬೇಕು. So miniaturization, it is called as compactness. Okay. So others layout area, this is called as area of the layout. Area ಏನಂತ ಇದರ ವೇಸ್ಟ್ ಜಾಗ ಕಡಿಮೆ ಮಾಡ್ಕೊಂತ ಹೋಗಬೇಕು, or that is the better design. So I have shown you different forms of the layouts. Okay, all these layers are of inverter only, but as I said, we should be very flexible in drawing the layouts depending on the conditions, which all signals or which all layers are passing through it, or how efficiently we can draw the layout of the circuit. In the same way, we have different layouts. Here what we have is, this is again inverter, but it is parallel inverter. So in this, how many inverters are there? 3 inverters are connected parallelly. P diffusion, P diffusion, P diffusion. P diffusion, P diffusion, P diffusion. One poly. So yes, transistor form on the 3 P MOSFETs. Okay. And see the connection. VDD is shorted to all the sources. And here all the drains are shorted to all the drains of NMOS. So here this is parallel inverter. Yes, parallel inverter layouts. So this is parallel inverter. There are more inverters they are connected in parallel. Sometimes it may be used. Okay. Some circuit rules and the we can use it. Even this is also similar kind, but the structure is somewhat modified. Okay. So here we have one diffusion, second diffusion, third diffusion, fourth diffusion. 4 parallel inverters are there in this. Okay. B. So here also, see, here correction check ಮಾಡಬೇಕು ನೀವು. ಇದು ಮತ್ತೆ ಇದು ನೋಡ್ರಿ. So it is connected parallelly, it is not two, and these two. So what we are doing, 1, 2, 3, 4. Now two sources of the PMOS are shorted to VDD, and these drains, confused are both. Sir, the other drain is one, but they are overlapped. This 1, 2, 3, 4 sources are. Either drain will be either drain will be so this one is drains, this one is drains. Totally 4 drains. All are shorted. Okay. So this is 4 inverter layout in parallel connection. Either what is this? So this is real diffusion. Okay. This is P diffusion. This is more complex one. So these are the sources. Then this is the drain. This is the drain which is shorted here. And coming down. So this is also drain. This is also drain. This is drain actually. And these are the sources. So 1, 2, 3, 4. 4 sources I have. Again 4 parallel inverters. 1, 2, 3, 4. ಹೌದಾ ನೋಡಿ ಇದು ಸೋರ್ಸ್ ಹೌದಾ ಈ ಸೋರ್ಸ್ because this is also P diffusion and this is also P diffusion. ಎರಡು P diffusion ಅದಾವು. ಈ P diffusion is one poly. Is one poly ಅಂತಂದ್ರೆ this is source, this is drain. Source and drain. is one P diffusion ಐತಿ ಇಲ್ಲೊಂದು poly ಬಂದು ಬರುತ್ತೆ. ಹೌದಾ ಈ poly ಬಂದ್ರೆ this is source, this is drain. So either drain common overlap. ಇಲ್ಲಿ ನೋಡಿ ಇದು P diffusion correct ಇಲ್ಲಿ ನಡಕ ಒಂದು poly ಬಂತು. So this is source, this is drain and ಇಲ್ಲೂ ಹಂಗೆ ಅದ. This is source, this is drain. So drain is 4 in 1 drain. 4 in 1 drain ಅದ ಇದು. 1, 2, 3, 4 sources. ನಾಲ್ಕು source ಚೆಕ್ ಮಾಡಿ VDD ಶಾರ್ಟೆಡ್ ಐತಿ. ಇಲ್ಲಿ ನೋಡಿ ಇಲ್ಲಿ ಕನೆಕ್ಟ್ ಆಗಿ VDD ಹೋಯ್ತು. ಇಲ್ಲಿ ನೋಡಿ ಇಲ್ಲಿ ಕನೆಕ್ಟ್ ಆಗಿ VDD ಹೋಗಿದೆ. ಆಮೇಲೆ ಇದು ಇಲ್ಲೇ ಇದೆ. So 1, 2, 3, 4 all these sources are shorted to VDD. 4 in 1 drain. It is shorted like this and brought down, and this PDM center this is also 4 in 1 drain. This is also 4 in 1 drain. E 1, 2, 3, 4. These are the 4 sources of NMOS which are shorted to ground. So 4 parallel inverters. Parallel inverters 4 in number. ನೋಡಿದ್ರೆ ಅಷ್ಟು ಈಸಿಲಿ ಅನ್ಸೋದಿಲ್ಲ, ಬಟ್ ಇಟ್ ಈಸ್ 4 in 1 parallel inverter. Okay. Next, so we are studying what? We are studying the physical design. The physical design what bರ್ತದ? Whenever you go to the layout, it is physical design. Okay. What is this? ಹೇಳಕ್ ಬರ್ದಾರ, ಬಟ್ ಸ್ಟಿಲ್ ನೀವು ನೋಡಿ ಅನಲೈಸ್ ಮಾಡಿ ಕೇಳಬೇಕು. ಈ ಸರ್ಕ್ಯೂಟ್ ನೋಡಿದ್ರೆ ನಿಮ್ಗೆ ನೆನಪಾಗಬೇಕು. Because this is solved in the class. 2 input NAND gate. This is 2 input NAND gate. How it is 2 input NAND gate? This is P diffusion. This is N diffusion. 2 polys are there, which are A and B. You know it. B, A and B. Next, what we are doing? Source of these two MOSFETs are shorted to VDD. So these two become drain. Both the drains are shorted. And brought down. So the drain to drain short that is the output. And this is drain. So drain source. Because this should be in series. NAND gate A dot P. NMOS should be in series. PMOS should be in parallel. Parallel connection. Series connection. So drain source is shorted to ground. This we have seen in our regular class. This is alternate layout of NAND gate. Idu one layout. So what is the gist or what is the summary of this class? In physical design, there is no any rule that I have to follow like this only, I have to draw layout like this only, okay, depending on the situation, we can adopt any layout, but those layouts should definitely follow the layout rules. or lambda based design rules. In lab we have DRC check. Other one match model layout. Inverter model line. Fine. Soon we will do it. When you do the schematic of inverter, you will do the transient analysis and you will check the waveforms. Okay. After checking the waveform, you should draw the layout and check with DRC. DRC means design rule check. Design rule check means all the lambda based design rules will be checked. You follow Madino, you know. You follow Madino, it will throw an error to you. So this is alternate layout of 2 input NAND range. Now this is how connection is done. They have taken 2 P diffusions because they should be parallel. This is poly, this is poly. So we need connection parallel like this. Then this is the input other. Okay, the input other. Next what they are doing? ಎರಡು sources ನೋಡ್ರಿ shorted to VDD. ಎರಡು drain short ಮಾಡಿದಾಗ ಎರಡು drain short ಮಾಡಿ ಏನು ಕೆಳಗೆ ಹೋಗೋಣ that is the output. Okay, this is the output and this is one end diffusion. Why only one diffusion, end diffusion? Because we know connection should be in series. So this is drain to drain short agada. Drain ಅಂದ್ರೆ source ಅಂದ್ರೆ drain ಅಂದ್ರೆ source is shorted to VDD. And drain to drain and short agada, that is the output. And like NAND gates, we have the NOR gate layout also. Same concept is it. थोड़ा याद करती हूँ. Even the hard difference ಇಲ್ಲ ಎರಡು ಲೇಯರ್ಸ್ ಗೆ ಏನು ಡಿಫರೆನ್ಸ್ ಅದ ನೋಡ್ರಿ ಇಲ್ಲಿ what they are doing this is in series NOR ಅಂದ್ರೆ PMOS in series so this is source drain to output okay that drain is shorted to this drain okay here we have both the drains so it's source drain so drain is shorted both the drains are shorted to upper drain. And here the parallel connection are equal to, therefore both the sources are going to the VDD. ಇದಕ್ಕೆ ಏನು ಡಿಫರೆನ್ಸ್ ಅದ ಅಂದ್ರೆ Indian drain short in center ಬಂದಿತ್ತಲ್ಲ here they are considering this as drain. Okay, so this drain is shorted to this drain. This drain is shorted to this drain. Okay, using different layer. So in metal one layer ತಗೊಂಡಾಗ this short ಏನಿಲ್ಲ ಈ source ಅದು actually. So this source is shorted directly to ground. So this is different layer. The different layer is a different layer. So there is a ply over there. Okay. So they are choosing the via. This via bರ್ತದೆ. So drain to drain short ಹಿಂಗ ಮಾಡ್ಯಾರ ಅವರು. And source ಎರಡು source ಕೆಳಗೆ ಬಂದು ground is shorted. So you should be remembering the layouts. ಅವಾಗ ನಿಮಗೆ ಇದು ಕ್ಲಾಸ್ ಹೌದು ಅನಿಸ್ತದೆ ಲೇಔಟ್ ನೆನಪಿಲ್ಲ ಬರ್ತಿದ್ದೀನಿ ಅಂದರೆ ಪ್ರಾಬ್ಲಮ್ ಆಗ್ತದೆ. Give the summary at least. So what is the summary? The summary ಏನೈತೆ ಅಂದ್ರೆ what is the summary of this? When MOSFETs are in series, resistance doubles. Therefore the time also doubles because T is equal to R into C. Okay, so in series is under R plus R 2R, so T will become 2R into C. And when MOSFETs are in parallel, the effective resistive resistance becomes R by 2. Therefore, T will be R by 2 into C. So, what is the summary of this? When MOSFETs are in series, okay, it takes more time or delay increases. When MOSFETs are in parallel, it takes less time. Okay. And this mismatch of timing can be compensated with width of the MOSFET. So when I get more delay, I have to increase the width of the MOSFET there, because by increasing the width of the MOSFET, we can reduce the resistance of the MOSFET. Okay. So resistance kadime ಮಾಡಬೇಕು ನೀವು ಅಂದ್ರೆ you have to increase the width of the MOSFET. So what is this graph? This graph is nothing but delay characteristics of cascaded gates. Delay characteristics of cascaded gates means what? How delay is increasing when I go on cascading the different gates. Okay. So m is number of gates. So if I have one gate cascaded, this is the delay. If I have two gates cascaded, this is the delay. If I have three gates or three MOSFETs cascaded, this is the delay. 6 MOSFETs cascaded, this is the delay. Okay. So the delay goes on increasing when I go on cascading the MOSFETs or gates. So I said how to compensate this delay. Increase the width of the MOSFET. Okay. Increasing the width of the MOSFET will reduce its resistance. So this graph will come down. But we need to compensate with the area. Okay. You width of the MOSFET jasti madidre jasti area togollude. But delay will be coming down. Okay. Next is we are seeing 3 diagrams. Logically, all 3 diagrams gives you the same output. Check ಮಾಡ್ಕೊಳ್ಳಿ. First one is 8 input NAND gate. 8 input NAND gate. Followed by inverter, followed by output. Second diagram is 4 input NAND gate and 4 input NAND gate. 2 4 input NAND gates. Third diagram 2 input NAND gates, but 4 in number. Okay. So now my question is whether all the 3 diagrams will give you the same delay or different delay. They will give you different delay. So I prefer you people doing this in the lab. Practically ಮಾಡಿದ್ರೆ you will learn a lot. So ಇದನ್ನ ಲ್ಯಾಬ್ ಒಳಗೆ ಮಾಡಿ ಅಂತ ಬಂದು ಹೇಳ್ರಿ ಯಾವ ಕೇಸ್ ನಿಮ್ಗೆ ಜಾಸ್ತಿ ಡಿಲೇ ಕೊಡ್ತದ, ಯಾವ ಕೇಸ್ ಕಡಿಮೆ ಡಿಲೇ ಕೊಡ್ತದ. ಯು ಕ್ಯಾನ್ ಆಲ್ಸೋ ಕ್ಯಾಲ್ಕುಲೇಟ್ ದಿ ಪವರ್ ಆ್ಯಂಡ್ ಎನರ್ಜಿ ಆಲ್ಸೋ. ಪವರ್ ಕನ್ಸಂಪ್ಷನ್ ಎಲ್ಲಿ ಜಾಸ್ತಿ ಅದ, ಎಲ್ಲಿ ಎನರ್ಜಿ ಕನ್ಸಂಪ್ಷನ್ ಜಾಸ್ತಿ ಅದ. ಹೌದು, ಭಾಳ ಸಿಂಪಲ್ ಐತಿ, ಬಟ್ ಕಲೀಲಿಕ್ಕೆ ಭಾಳ ಐತಿ. ಯಾಕೆ ಹಂಗದ ಆಮೇಲೆ ವಿಚಾರ ಮಾಡೋದು. ಆ್ಯಕ್ಚುಲಿ ಪ್ರಾಜೆಕ್ಟ್ ಸ್ಟಾರ್ಟ್ಸ್ ಆಫ್ಟರ್ ಗೆಟಿಂಗ್ ದಿ ಔಟ್ಪುಟ್. ನೀವೇನು ಮಾಡ್ತೀರಿ, ಔಟ್ಪುಟ್ ಬಂತ ನಡಿ ಮುಗೀತು. ಪ್ರಾಜೆಕ್ಟ್ ಸ್ಟಾರ್ಟ್ಸ್ ಆಫ್ಟರ್ ಗೆಟಿಂಗ್ ದಿ ಔಟ್ಪುಟ್. ಯಾಕೆ ಹಿಂಗ್ಯಾಕೆ ಬಂತು ಇದೆಲ್ಲ ವಿಚಾರ ಮಾಡಬೇಕು. ಸೊ ದಿಸ್ ಯು ಕ್ಯಾನ್ ಟೇಕ್ ಇಟ್ ಆಸ್ ಹೋಮ್ವರ್ಕ್ ಫಾರ್ ಲ್ಯಾಬ್ ವರ್ಕ್, ರೈಟ್? And get back to me with some results. ಇದರೊಳಗೆ ಯಾವ ಚಲೋದ ಡಿಸೈನ್ ಅಂತ ಬಂದು ಹೇಳ್ರಿ. Next is body effect. Body effect. So what is body effect? We have already seen it. What is body effect? When source voltage and the body voltage are different. When the source is not shorted to the body, it causes body effect. When source ಒಂದ್ಸಲ ಲಕ್ಷ ಕೊಡ್ರಿ, ಈಗ ಯಾವ ಗೇಟ್ ಅಂತ ಕೇಳಿ ಫಸ್ಟ್. Now get each other. 4 input character. NAND or NOR? NAND or NOR? NAND, because they are in series. Dot means in series. 4 input NAND. Correct. Now 4 input NAND gate. If you observe keenly, ಈ MOSFET ನೋಡ್ರಿ, ಇದರ ಸೋರ್ಸ್ ಅಲ್ಲಿ ಇಲ್ಲಿ ಹೌದು, ಇದರ ಬಾಡಿ ಏನೈತಿ ಇಲ್ಲಿ, this is the body. So body is shorted to the source. ಆ MOSFET ಅದ ಬಾಡಿ ಮತ್ತೆ ಸೋರ್ಸ್ ಶಾರ್ಟ್ ಆಗ್ಯಾವ. ಅಲ್ಲಿ ನನಗೆ ಬಾಡಿ ಎಫೆಕ್ಟ್ ಕಾಣೋದಿಲ್ಲ, because voltage at the body and voltage at the source are same. ಎರಡು ವೋಲ್ಟೇಜ್ ಸೇಮ್ ಅದಾವ. ಬಟ್ ನೆಕ್ಸ್ಟ್ MOSFET ಚೆಕ್ ಮಾಡ್ರಿ, ನೆಕ್ಸ್ಟ್ MOSFET ಸೋರ್ಸ್ ಇಲ್ಲೈತಿ ಕೆಳಗಿಂದ, ಬಟ್ ಅದರ ಬಾಡಿ ಎಲ್ಲ ಹೋಗಿ ನೋಡ್ರಿ, ಇಲ್ಲಿ ಶಾರ್ಟ್ ಆಗೈತಿ. this source is shorted to drain of this, but body is shorted to ground. So VB is 0, but VS may not be 0 or may be 0, I don't know. If this MOSFET is on, then it will be 0. If this MOSFET is not on, then it may not be 0. Okay, ಇಲ್ಲಿ explain ಮಾಡ್ಯಾರ ನೋಡಿ. So they have taken the Vc1. What is Vc1? Voltage at C1. What is C1? What is C1? Capacitance. Okay. So they are just plotting the graph of this voltage along with all the inputs. Okay. How interesting is that?